Section 5.2, integral and net area. In section 5.1, all the functions are assumed to be non-negative. For a non-negative function, its graph lies above the x-axis, and the integral of a non-negative function from a to b is the area of the region under the curve, under the graph of the function, and above x-axis and between a and b. Now, in today's section 5.2, functions can be general functions. A general function means the function can take on both positive and negative values. For a general function, the integral of the general function from a to b, now this time, is the net area of the region between the graph of the function and x-axis and between a and b. Here is a diagram of the region. The region between the graph of the function and x-axis and between a and b is the shaded region here. Net area of this region means the total areas above x-axis minus the total area below x-axis. In this diagram, total area above x-axis is this area plus this area. And total area below x-axis is this area. When a function is a general function, integral is net area. Area above, total area above x-axis minus total area below x-axis. To understand that the integral of a general function is equal to the net area of the region S, we need to review the definition of an integral. Here in this diagram, we have a curve. This curve is the graph of some general function. Part of the curve is above x-axis and part is below x-axis. To compute this integral by definition, step one, we need to evenly cut the interval AB into subintervals. In this diagram, I have cut the interval AB into 13 subintervals. Now step two, over each subinterval, build one rectangle. Over the first subinterval, arbitrarily pick a point, x1 star, and use the function value at the point as the height to build this rectangle. Over the second subinterval, arbitrarily pick a point and use function value at the point to build a rectangle, and so on. Rectangle 1, rectangle 2, rectangle 3, rectangle 4, rectangle 5. Over the fifth subinterval, arbitrarily pick a point. Then use the function value at the point to build a rectangle. Now this time, because function value is negative, so the rectangle, the fifth rectangle, lies below x-axis. The sixth rectangle also lies below x-axis because function value at the point here is negative, so the height negative, so below x-axis. Okay, now build up rectangles. Now, step 3. Sum up the areas of all the rectangles. First rectangle area, base delta x times height, function value at x1 star. Second rectangle, base times height, function value at x2 star. Third rectangle, base times function value at x3 star. And the fourth rectangle is base times function value at x4 star. The fifth rectangle is base times function value at x5 star. Pay attention. Function value at x5 star is negative. Function value at this point, negative. So, negative number times base, this is a negative number. The product is negative. But area of a rectangle is always a positive number. So actually, this product is -1 times the area of this rectangle. Similarly, function value at x6 star is negative. Yeah, negative. So this product is a negative number. But this rectangle, the sixth rectangle area is positive. Area is always positive. So this product actually is equal to -1 times the area of this rectangle. Similarly, for the 7th rectangle, for the 8th rectangle, and for the 9th rectangle. For the 10th rectangle, the 10th rectangle is here. I pick a point, and then function value at this point is positive. Can you see that? Positive. So function value at this point times base, it is a positive number. It is the area of this rectangle. Okay, now here this equation, AR1 means area of rectangle 1. Yeah, the first term is area of rectangle 1. Second term, area of rectangle 2. Third term, area of rectangle 3. This is a rectangle 4. And this is rectangle 5. But this number is negative, so it is a negative area rectangle 5. And also this is a negative number, so negative area rectangle 6, negative area rectangle 7, and so on. And then this is function value at this point positive. Positive times base, it is area of the 10th rectangle. This is an area of the 11th rectangle, and so on. Now, let me take out the negative sign for these 5 rectangles. Then I get this equation. From this diagram, rectangle 1, rectangle 2, rectangle 3, rectangle 4, the sum of their areas is approximation of this region. This region lies above x-axis. And similarly, area of rectangle 10, 11, 12, and 13, these 4 rectangles, the sum of their areas is an approximation to the area of this region. This region lies above x-axis. Now, this region plus this region is the total region that lies above x-axis. So, this sum and this sum together roughly is the total area above x-axis. How about the middle term? Area of rectangle 5, rectangle 6, 7, 8, and 10. Their sum. The summation of these areas roughly is the area of the region below x-axis. So minus A below. A below means that the total area below x-axis. Okay. So summation of the areas of all the rectangles roughly is total area above x-axis minus total area below x-axis. Now, to make this approximation into an equation, we need to increase the number of rectangles. Here in this diagram, only 13 rectangles. Increase the number of rectangles to infinity. Then this sum here, this sum will approach area above minus area below. That means that will approach the net area. So when we let n, the number of rectangles approach infinity, then the limit of this sum, okay, the sum here, yeah, the limit of this sum is equal to total area above x-axis minus total area below x-axis. But this limit, by definition, is this integral. So that's why we say that when a function is a general function, integral of the function from a to b is net area of the region between the graph of the function and x-axis and between a and b. Now, let me show you some examples about this formula. This formula says that integral of a general function is net area. Example 1. Use geometry, not the definition, to evaluate the definite integrals below. Use geometry, not the definition. Definition is tedious, right? 4 steps. You need to, to compute an integral, you need to cut the interval AB into subintervals, then build rectangles, then sum up areas of the rectangles, then compute limits. Compute the limit, right? Very tedious. So don't use the definition to find the following definite integrals, but use geometry. That means that use this formula to find the following integrals. Sketch the graph of the integrand. What is integrand? The function f is called the integrand of the integral. Sketch the graph of the integrand. So the region in question. So the region that is between the graph of the function and x-axis and between a and b. And interpret your result. Okay, now first integral. Take integral on cosine from 0 to 2 pi. Okay, now the integrand of this integral is cosine. Here is the graph of cosine. Graph of cosine. This integral is the area of the region between the graph of cosine and x-axis and between 0 and 2 pi. The region is the shaded region here. Okay, so this integral is the net area of the shaded region. Okay, it is total area above x-axis minus total area below x-axis. Total area above x-axis is this area plus this area. This area plus this area clearly is equal to the area below x-axis. The area below x-axis. So therefore, area above minus area below is 0. Therefore, this integral is 0. Now, B. Find the value of this integral. The integrand is 2x plus 3. Okay, now let me plot the graph of 2x plus 3. The graph is a 9. It's a 9. Okay, 9. Okay, now this area is that area of the region between the graph of the function and x-axis and between 2 and 4. The region is this shaded region here. Shaded region here. Okay, now integral is area above minus area below. This region, area above x-axis is this, the region is a trapezoid. Then how to find the area of a trapezoid? There is a formula. There is a formula for the area of a trapezoid. And if you don't remember the formula of trapezoid, it doesn't matter. You can, cut the trapezoid into a triangle. Yeah. Okay. Draw a line through this point, parallel to x-axis. Then this line will cut the trapezoid into a triangle and a rectangle. This triangle, the area is 1/2 times base. Base from 2 to 4. The length is 2, so base is 2. Height, this triangle, the height from 7 to 11, the height is 4. So this is the area of the triangle. Then the rectangle here, the area is base 2 times height. Height is 7. So area of triangle plus area of rectangle is the area of this trapezoid. Minus 0, because total area below x-axis. This trapezoid has low area below x-axis. So A below is 0, so minus 0. So the result is 18. So this integral is 18. Now, the third integral, find the value of this integral. The integrand is 2x minus 6. Again, the graph is a 9. Okay. Now here, 2x minus 6. The graph is this 9. This 9. The region between the graph of the function and x-axis and between 1 and 6. 1 and 6 is the shaded region here. The shaded region here. This integral is that area of this shaded region. Total area above minus total area below. About this region, the total area above x-axis is this triangle. The area of the triangle is 1/2 times base. Base is 3. And times height. Height is 6. Height is 6. So this is an area above x-axis. Minus area below x-axis. Area below x-axis is the area of this triangle. Base is 2 from 1 to 3. The length is 2. Base is 2. Height from 1 to -4. Height is 4. So area of this triangle is this number. So area above minus area below is 5. This integral, the value is 5. Integral in D, yeah, integral in D. The function is quite complicated. It turns out that the graph of this function is part of a circle. To see that the graph is part of a circle, let me denote the function by y, okay? Denote the function by y, okay? Now, to see the graph of this function is part of a circle, let me transform this equation into a circle equation, Take square on the both sides. Then we get this equation. And then move this term to the left side, then we get this equation. You see, this equation is a circle equation. A circle, the center of the circle is 3, 0, 1 minus 0, so 3, 0. The center is 3, 0. The radius is 1. 1 is 1 square, so 1 here. Radius is 1. Center is 3, 0. Yeah, this circle. This circle is the equation. This circle is the graph of this equation. This equation actually contains two functions. One function is this. Yeah, one function is this. Second function is this. Second function is this. The graph of this function is upper semicircle. The graph of this function is lower semicircle. Now, this integral from 3 to 4, this integral is the region between the graph of this function, circle, and x-axis, and between 3 and 4. So the region is this shaded region. So this integral is the net area of this region. A above minus A below. A below, this region has no part below x-axis. So A below is 0. A below is 0. A above, area above x-axis. Area above x-axis is a quarter of the area of this circle. So area of this circle is pi r square. R is 1, so the area of this circle is pi. Okay, a quarter, 1/4 of pi, so pi over 4 is total area above x-axis. So pi over 4 minus 0 is pi over 4. So this integral, the value is pi over 4. One more example about this formula. For the function f, whose graph is so below, list the following quantities in increasing order and explain your reasoning. To list the quantities from the smallest to the largest, we need to know roughly the values of the quantities. Now, let me guess on the values of these quantities. First, take a look at this integral. This integral is the net area of the region between the graph of the function and x-axis and between 0 and 8, By formula, this integral is area above the x-axis minus area below the x-axis. Area above x-axis is this area. Let me use this triangle to approximate the area. This triangle, the base is 5. From 3 to 8, the base is 5. The height is 4.5. So area above is this number, 1/2 times space times height. Area below is this area. Again, I use a triangle to approximate this area. The triangle is this triangle. The height is 2. The base is 3. So area of this triangle is 1/2 times base times height. So therefore, this integral is roughly 8.25. Now, the second integral. Second integral is from 0 to 3. From 0 to 3, it is the net area of the region between 0 and 3. This region has no part above x-axis. So A above is 0. A below is this area. I use this triangle to approximate it. So again, A below roughly is this number. So 0 minus this number is -3. So roughly, this integral is -3. Now, the third integral. The integral is from 3 to 8. So this is the net area of the region from 3 to 8. This region has no part below x-axis. So A below is 0. Area below x-axis is 0. Area above x-axis is this area. I use this triangle to guess on this area. So the area of this triangle is this number. Therefore, this integral from 3 to 8 roughly is 11.25. Now, the fourth integral. Fourth integral, integral from 4 to 8. 4 to 8. This is the net area of the region between 4 and 8. This region has no part below x-axis. So area below x-axis is 0. Now, how to find area above x-axis? Yeah, area above x-axis is the area between 4 and 8. Yeah, this area. Then how to get this area? This area between 4 and 8 is the area between 3 and 8 minus the area between 3 and 4. Area between 4 and 8, I can use this triangle to approximate it. Area between 3 and 4, I can use this smaller triangle to approximate it. This smaller triangle base is 1, height is 2. So therefore, area above is area of the bigger triangle minus the smaller triangle. The bigger triangle is this triangle. Smaller triangle is this triangle. So therefore, the integral from 4 to 8 roughly is 10.28. Finally, guess on this derivative f1. Recall that derivative is slope of tangent line. So draw a tangent line to the graph of the function f1. Draw a tangent line. And guess on the slope of the tangent line. Roughly, it is -1. So this quantity is roughly -1. Okay, now with this information in hand, then I can make a list from the smallest to the largest of these quantities. The smallest quantity is integral from 0 to 3. It is about -3. So this one smallest. The second smallest quantity is derivative at 1. The third smallest quantity is integral 0 to 8, roughly 8.25. Now, the last one is integral from 4 to 8. The largest quantity is integral from 3 to 8. 3 to 8 roughly is 11.25. Here is the last example. This example is about the definition of integral. Consider this function on this interval. Question A, sketch the function on the given interval. The graph of this function is a parabola, open downward, because the coefficient of the x squared term is negative, so the parabola is open downward. The parabola intersects x-axis at 2. Question B. Approximate the net area bounded by the graph of the function and the x-axis on the interval using a midpoint Riemann sum with 4 rectangles. The region between the graph, between the parabola and x-axis, and between 0 and 4 is this shaded region. Now, according to question B, we need to use 4 rectangles to approximate the net area of this shaded region. First, we cut the interval 0 to 4 into 4 subintervals, evenly cut. The length of each subinterval is delta x. By formula, it is b minus a over n. B now is 4, a is 0, and n is 4. So the length, delta x, is 1. So the length of each subinterval is 1. The cutting points, x0 is always the left endpoint of the interval. Now, in this example, the interval is 0 to 4, so x0 is 0. x1, this point is x1, it is 1. This is a 2, x2, x3 here. x4 is the last cutting point. The last cutting point is always be the right endpoint of the interval. It is 4, okay. Now, build rectangles. Use function values at midpoints. Over the first subinterval, pick midpoint. Between 0 and 1, the midpoint is 0.5. Function value at 0.5 as height to build a rectangle. The area of this rectangle is delta x times the function value. Over the second subinterval, the midpoint is 1.5. So function value at 1.5 is the height of the rectangle. Area is base delta x times function value at 1.5. The third rectangle, between 2 and 3, pick the midpoint, 2.5. Function value at 2.5 as height to build a rectangle. Now, because function value at 2.5 at this point is negative, this rectangle lies below x-axis, and also pick midpoint between 3 and 4. Function value at this midpoint as height to build the fourth rectangle. The fourth rectangle also lies below x-axis because function value at this midpoint is negative. Okay, now sum up this area, these areas. Okay, factor delta x out. Then we get this equation. Now plug in the values in delta x and into these function values. Delta x is 1. Function value at 0.5. Function, this is the function. Plug in 0.5 in x, then we get function value is 7.5. Also, function value at 1.5 is 3.5. Function value at 2.5, now 2.5 here, now negative 4.5. And then this function value also negative 16.5. Now calculator, then we get negative 10. So if use 4 rectangles and build rectangles with function values at midpoints, then the net area is roughly negative 10.